Hey, welcome back. It's Kevin Wallace again. We've already talked about the first two layers of the USL model now. We talked about the physical layer. That's where things like a hub would live. That's where our wiring standards reside. We've talked about the data link layer. That's where an Ethernet switch lives. And we saw that it had two sub-layers, the MAC and the LLC sub-layer. Time to move up to layer 3 right now. And at layer 3, we're concerned about several things that a lot of people don't always think of. Check out this graphic. Notice at layer 3, we're concerned with logical addressing, switching, route discovery and selection, and connection services. Logical addressing, that's what a lot of people think of at layer 3 because it's here where we logically assign a network address. We've got different routable protocols like IP, that's the one that we typically use in most networks today. IP, that's the Internet Protocol. But back when I used to work for a local university, we would route not only IP, we would route AppleTalk, and we would route Novell's IPX. However, today, both Novell and Apple, they're using IP primarily to route their traffic. So IP by far has become the predominant layer 3 protocol out there. And we're going to have different layer 3 addresses as we're going to discuss in a future video. And we're going to be able to intelligently forward or route traffic between these different logical networks that are defined here at layer 3. And you might be surprised to see the term switching here when we talk about layer 3 because we think of switching typically as a layer 2 concept, but switching can mean packet switching as an example. That's something that does happen at layer 3. With packet switching, our data is divided into packets, and these packets have a header saying where the packet came from, where the packet is destined, and a device called a router is going to intelligently switch. It's going to packet switch that packet towards its destination. There's also at layer 3 the concept of circuit switching. That's where we can dynamically bring up a circuit on demand and then tear it down when we're done. Think of that as being somewhat analogous to placing a phone call. You pick up a phone, you call somebody's phone number, and when you're done, you tear down the circuit. That's circuit switching. There is also message switching. Here, our data stream is divided into different messages. And these messages, much like a packet, have a destination address, but they're not necessarily immediately sent to that destination address. It's almost as if we're sending email from one email server to the next. In other words, the next hop device on the way to a destination, a message might be stored. And at the next device, it might be stored for a while before it's forwarded. This store and forward approach to forwarding messages through a network is not great for real-time traffic, obviously, but it is a method. Primarily, though, in the networking world, we are concerned with packet switching. We have source and destination IP addresses on our packets, and we packet switch those packets. In other words, we route those packets towards their destination. Something else going on at layer 3 is route discovery and selection. We said that a device called a router resided at layer 3, and that router is going to make intelligent forwarding decisions. Remember how a switch worked down at layer 2? Down at layer 2, a switch made forwarding decisions based on physical MAC addresses. That's the way an Ethernet switch worked. However, with routing at layer 3, we're making forwarding decisions based on destination IP addresses typically. How does a router learn how to get to specific destination IP addresses living in specific destination IP networks? Well, there are a few ways. We might have a network that's directly attached to a router interface. By definition, a router knows that it knows how to get to this network. It's part of the network. We could alternately go in and statically configure a route. We could say to get to this network, you need to go out of this interface, or you need to go to this next hop IP address. Or we could run a routing protocol, something like OSPF, RIP, EIGRP. A dynamic routing protocol can educate the router as to how to reach a destination network. So we've got those three primary ways of learning routes and selecting routes inside of a router. Again, directly attached networks, statically configured networks, or dynamically learned networks. And also at layer 3, we have connection services. And here I think about things such as flow control and packet reordering. Flow control can actually happen at more than one layer of the OSL model. This is just one layer where flow control can happen. The idea behind flow control is that if a sender is sending too rapidly, A flow control mechanism can ask the sender to slow down, to stop sending so rapidly so we don't overflow the destination circuit or we don't overflow the buffer in a router along the path. We're wanting that sender to slow down a bit. And we've been discussing some of the things that theoretically reside at layer 3, but to get very real world and to get very practical, let's remember that primarily we're dealing with IP addressing at layer 3, and we're dealing with packet switched networks. Let's take a look at the header format of an IP packet. Check out this graphic. There are several interesting fields here in this graphic. Let's talk about a few of them. Notice that we have source address and destination address fields. It's here in an IP version 4 packet where we have a 32-bit IP address saying where the packet's coming from, where the packet is destined. There's also a TTL, a time to live field. Every router that we transit, every router hop that a packet goes through, this TTL value gets reduced. It gets decremented by 1. And once it reaches a value of 0, it's considered to have timed out. And an error message gets sent back to the sender saying, sorry, this packet is timed out. This is actually a very good thing. This can prevent a layer 3 topological loop from forming and endlessly circulating a packet around and around the network. We don't have this luxury at layer 2. Down at layer 2, there is no time to live value in a frame header, and as a result, we can get endlessly circulating frames at layer 2. That's why we need something like the spanning tree protocol to break a layer 2 topological loop. But we do have it at layer 3. What else is going on here at layer 3? Notice the protocol field. The protocol field is pointing up to layer 4. It's saying we're communicating with a certain protocol at layer 4. That's the topic of our next video. At layer 4, we're going to see protocols such as TCP and UDP. Those are a couple of the major protocols up at layer 4, and we can have a protocol identifier down here in our layer 3 packet header to say what layer 4 protocol we're communicating with. And one other one we'll take a look at is the TOS, the type of service field inside of this packet header. This is for quality of service. We can go in and typically we're going to use the 6 leftmost bits in this 8-bit field to indicate a priority value of a packet. That's a theory overview at layer 3, but let's take a look at what's going on hardware-wise. We said that we might have a router operating at layer 3. Well, here's a fairly old router from Cisco. You see that we have a few different ports along the front. I've got a couple of serial connections that might connect out to a WAN service provider. I've got an Ethernet port that might connect to the local area network. And each of these ports can be assigned a separate IP address. They live in separate IP subnets. And therefore, if I were to assign a different IP subnet to these 3 different interfaces, the router already knows about 3 networks that it could reach because they're directly connected. I could administratively go in and say, if you want to get to the 192.168.5.0/24 network, go out of this Ethernet port as an example. Or there could be other routers in my topology that I'm exchanging dynamic routing protocol information with. How do we take a look on this Cisco router at what routes we know about? Let's go out to our terminal session and check it out. We could give a command like this. We could say show IP route. And this is going to tell us about the routes that we have learned. And notice that they are flagged with their source. Notice that we have an O next to some of these routes. There's a C next to some of these routes. The O means we have dynamically learned this route via OSPF. The C means we've learned this route to this network because it's directly connected to the router. In fact, on this router, I've got a few L's showing up as well. L means local. This is an IP address assigned to one of my router interfaces, my sub interfaces, my VLAN interfaces. So you see those occasionally, but primarily I want you to focus on the C's for directly connected, the O that I've learned via OSPF, a dynamic routing protocol. And I don't have any statically configured routes right now. We could add one easy enough though. We could go into global configuration mode and we could say IP route, and maybe I want to get to the 172.16.1.0 network with a 24-bit subnet mask. And I could say, to get there, I want to go over to a next hop address of, let's say, 10.10.32.1. .1 as an example. Now, if we go back and we look at our IP routing table with another show IP route command, in addition to the O's and the C's and the L's, notice that there's now an S. That's a statically configured route. Those represent the three ways that we talked about of educating a router as to how to get to different networks. We might be directly attached, connected, we might statically configure a route, or we might dynamically learn a route. Well, that's going to do it for our Layer 3 discussion. We'll see you next time as we take a look at the protocols residing at Layer 4.